the recording has started. Okay. Is the screen visible?
Yes.
Okay, thank you. So, I welcome you all to the third week of the live sessions for the course Basics of Finite Element Analysis Part 2. The course instructor, as you may all know, is Professor Dr. Nachiketa Tiwari from IIT Kanpur. Once again, introducing myself, I am Vikram Balaji, research scholar from the Department of Mechanical Engineering at IIT Madras. So, this is the third week. So, we had 2 weeks. Last Monday and last to last Monday. So now we are going to have the third week. So this session will be pertaining to solving of sample assignment questions related to the lecture contents of the third week. So we will simply recall what we learnt in the week 3 contents. So firstly, we might have seen some introduction to numerical integration schemes. So after that, we saw some types of approximations, and then we saw about briefly some types of formulation, and then we saw about what is known as Gauss Legendre quadrature. So these were the four main
Your
topics.
voice is getting break.
Uh, is it now audible?
Yes.
Okay, I think somebody has switched on their mic, because of which there may be some echo. So if there is anybody, so whenever you want to ask something, or if I ask you to respond, you can open the mic during that time. Otherwise, it's better to keep it closed, because there may be some echo when I am talking. So now it's all right. Am I audible?
Yes, perfectly all right.
Okay, thank you. Okay, so coming back, so these were the four main topics which were covered in the week 3 contents of the lectures. So we'll just see some set of 15 to 16 sample questions. So through these questions, it will be a combination of both objective and subjective. So this will help you to recap the concepts of what we learned in the week 3 contents. So let us move on to the questions. So this is the first question. So the order of interpolating function used in the trapezoidal rule and Simpson's rule of numerical integration schemes are respectively. So we have two interpolating the order of interpolating function. So we have two numerically integration schemes which are specified here. One is the trapezoidal rule, another is the Simpson's rule. So what are the orders of the interpolating functions which are used in these two numerical integration schemes? So there are four options given. Option A is 0 and 1. So which means 0 corresponds to trapezoidal, 1 corresponds to the Simpsons. Option B 1 and 2. Option C 2 and 1. Option D 1 and 0. So can anybody guess as to what could be the right answer? Any guesses? So once again, I am repeating. So we have two numerical integration schemes which are referred to here. One is the trapezoidal rule and another is the Simpson's rule. So in both the cases, they use interpolating functions to calculate the integration. So what is the order of the interpolating function which is used?
A01.
Okay, so one of the his thing is A01. So, okay. So any other guesses by anybody? Okay, so we shall proceed to look to the answer. So the answer is B. So answer is B 1 and 2. So we'll just recall what is a trapezoidal rule. So when you have a domain like this from A to B, so let us say this is x. So let us say the value of x here is xa and here it is xb, or let us or maybe 1 second, let us keep it as a and b for simplicity. So what does trapezoidal rule state? So trapezoidal rule states that your integral f of x dx. So let us say a function varies from a to b. From a to b is equal to, you can so I am defining the h as the length of the element. So length of the element, so h by 2 into f of a plus f of b. So this is a trapezoidal function. So do you agree? So any doubt in this formula which I stated for the trapezoidal rule? So a and b are my 2 points on the element, and I want to integrate an f of x from a to b. So this will be my approximation given by the trapezoidal rule. So let me write Simpson's rule now. So for Simpson's rule, we assume another point in the between, in the midpoint. Let us say it's a plus b by 2. So integral a to b f of x dx is equal to, so you will get something like h by 6 into f of a plus 4 times of f of a plus b by 2 plus f of b. So how we are getting these values? That is what is the question, right? So how we are getting these values is basically, when you are assuming f of x a to b, so this will be your, let us say this is your original graph. So what trapezoidal rule does is, it only uses the value at the end. So because of which, with two points, you can do only a linear interpolation like this. So that is what trapezoidal does. But in the case of Simpsons, so let me choose another color. So you have 3 points for interpolation. So what Simpsons does is, it chooses another point which corresponds to the midpoint a plus b by 2, and it does a quadratic interpolation like this, which passes through the endpoints and this midpoint. So you can say that linear interpolation is of order 1, quadratic is of order 2. So I hope you understand why B is the answer, which means that order of interpolating function used is 1 for the trapezoidal rule and it is 2 for the Simpson's rule. So any doubts? The first question. Hello? So any doubts? So just
Sorry, you can go ahead without unmuting and speaking.
okay, sorry. Okay, fine. No problem. So one second. Yeah. So answer is B. So we just saw how the interpolating, the interpolating function order is used is 1 for the trapezoidal rule and 2 for the Simpson's rule. So how the order is established is by this way. So in the trapezoidal rule, we are concerned only with the endpoints and we are interpolating the function through linear, and for the Simpson's rule we are interpolating through the quadratic function, assuming the midpoint also. So let us go to the second question. So now using the trapezoidal rule, find the area under the curve y is equal to x square. Let me choose the pen. So it's given y is equal to x square between x is equal to 0 and x is equal to 4 with element size of 1. So how to do this? So I have a function y is equal to x square. X square dx is going to be the area of the curve. So let us say we are having like this, y is equal to x square. So from 0 to 4 is our domain. So we have to calculate the area of the curve using trapezoidal rule, and with the element size of 1, which means what I am basically doing is I am going to split the domain into 4. So it's like this. So 0, the endpoint is 4. So you have 1, you have 2, you have 3. So I'll choose another color now. Basically, at each level you are going to do a linear interpolation. And calculate the green color area. So this green color area may or may not be equal to the original area under the red color curve. So let's recall the formula once again. So I am splitting the integral I is equal to integral 0 to 4 x square dx. I am splitting into 4 intervals, 0 to 1 x square dx plus integral 1 to 2 x square dx plus integral 2 to 3 x square dx plus integral 3 to 4 x square dx. Just erase the small part. Yes. So this one I call it as I1, this one I call it I2, this one I call it I3, this one I call it I4. So each I1, I2, I3 and I4 I am going to calculate using the trapezoidal rule. So for that what I am going to do, I need the function value at the endpoints of each interval. So which means I need the function value at 0, I need the function value at 1, then I need the function value at 2, then at 3, then at 4. So we'll quickly just I think I have to hold it this. So we'll quickly just see what are the values. I'll maybe erase this part. I'll just write in the top for now. I'll use black color only, that's better, or rather I'll use red. Okay, so f of 0 is equal to 0, f of 1 is equal to 1 square is equal to 1, f of 2 square is equal to 4, f of 3 is equal to 3 square is equal to 9, f of 4 square which equal to 16. Okay, so now I1 is equal to so what is I1? So again I recall the trapezoidal rule formula, integral of a to b f of x dx is equal to b minus a by 2. So h is equal to b minus a, element length. So b minus a by 2 into f of a plus f of b. So this is how you recall the trapezoidal rule. So for I1 it will be 1 minus 0 by 2 into f of it will be f of 0 plus f of 1. So this will be 1 by 2. So I2 is equal to 2 minus 1 by 2 into f of 1 plus f of 2. So how much is this? So this will again be 1 by 2 into some f of 1 is 1, f of 2 is 4, so 5 by 2. Okay, so I3 similarly 1 by 2 into f of 2 plus f of 3. So this will be f of 2 is 4, 4 plus 9, 13, 13 by 2. And I4, I'll write it here. So in all the cases b minus a by 2 will be 1 by 2. Why means in every case the elements width is 1. So 4 minus 3 by 2, which is again 1 by 2 into f of 3 plus f of 4. So which is equal to 16 plus 9, which is 25. 25 by 2. Okay, so I is nothing but I am going to add all the 4, I1 plus I2 plus I3 plus I4. So half plus 5 by 2 plus 13 by 2 plus 25 by 2. So your numerator, so your denominator will be 2. In the numerator you will have 1 plus 5 plus 13, then you have 25. How much is this? 5 plus 1 6, 6 plus 13 19, 25 plus 19 44 by 2 equal to 22. So yes, we have got the answer. Answer is 22. So now we can also check whether this is true with the exact integration. So exact integration, how you do? It's just simple, right? So 0 to 4 x square dx. So this is just x cube by 3. Integral of x square is x cube by 3 from 0 to 4. So at 0 is 0, at 4 you have 4 cube, which is 64. 64 by 3 is the exact value. You can see that there is a difference. So 64 by 3, it is something around 21.33. It goes on, 333 keeps repeating. So 21.33 and 22, there is a small error actually. This error is actually due to this approximation of linear. In the real sense, if you see, the curve is quadratic, but since we have to find the area by trapezoidal rule, we assumed a linear interpolation between each element, and finally we got a close answer, but which is nevertheless which is not accurate though. It's close enough, but not the exact answer. So we got as 22. Okay, so I hope there is no doubt in question 2. So shall we go to the next question? Alright then. So we'll go to the next question. Okay. So the question is, in Simpson's rule of numerical integration over a domain shown below, what are the quadrature weights associated with the function value at the end nodes, given h is the length of the domain? So what are the quadrature weights? H is the length of the domain, which means this value is h. So can anybody answer? Options are A h, B is h by 2, C h by 3 and D is h by 6. So can anybody guess as to what is the answer? Okay, the recording is on. We'll try to solve this now. So before that, any guesses as to what could be the answer? We saw the Simpson's rule formula in the first question. Any guesses? Okay, we'll now try to solve Simpson's rule. Yes, sir. So integral a to b f of x dx. This is approximated as h by 6 into f of a plus 4 times f of a plus b by 2 f of b. So we already saw that this formula arises because we are doing a quadratic interpolation. So you are interpolating the f of x using a quadratic function. So that takes into account the values at the end nodes a and b, and also at the value of a function at the midpoint, so which is a plus b by 2. So that is what is written here. So if you see the quadrature, if you split this further, you can see h by 6 times of f of a plus 4 h by 6 for f of a plus b by 2 plus h by 6 into f of b. So you can see that I have 4 function for the value of the function at 3 places. So I can circle this in orange. These are f of a, these are f of a plus b by 2, and this is f of b. So these are known as function, the function value. Function value at quadrature points. So what are quadrature points? The points at which the the functions are being computed. So those are called as quadrature points. So if I take another color, maybe green, and I circle these coefficients, this is h by 6, this is 4h by 6, this is h by 6. Okay. So these coefficients are called as quadrature weights. So function value at quadrature points and quadrature weights. Though in the question it is asked, what is the quadrature weight associated with the function value at the end nodes? So end nodes is nothing but a and b. So the coefficients of f of a and f of b, you can see both are h by 6. So that means answer should be D, h by 6. So D is the answer. So I think this question also, I hope there is no doubt. So we saw what is the formula of the Simpson's rule, and using the formula of Simpson's rule, we just found out what are the quadrature weights associated with the function value of the end nodes. Okay, so I'll go to the next question now. Hello, yes.
We have 4 by 6. But we
Yes.
have 4 by 6 in the middle, right?
Sorry, I didn't get your focus is on.
We have 4 h by 6 in the middle, right?
Yeah.
So how can I just h by 6 this?
So I'm just associated with the I mentioned in the question, right? So the quadrature weights associated with the function value at end nodes. So my question is only end nodes. Of course, there is 4h by 6, that is for the midpoint.
Okay,
So that is for yeah. So but we are only function value at the end nodes. So that you can see both are h by 6. So answer is D. So I hope doubt is clear. So we'll go to the next one. So this is a numerical. So using the Simpson's rule, find the area under the curve y is equal to 2x cube minus 4x plus 1 between x is equal to 2 and x is equal to 4 with element size of 1. I'll slightly what I'll do. I'll note down this question. I'll go to ever OneNote for writing, so that is actually more comfortable. So if you want to just it's Alt tab. So Simpson's rule, find the area under the curve y is equal to 2x cube minus 4x plus 1. So y is equal to 2x cube minus 4x plus 1. So this is actually much more easier because there is lot of space. So I have to integrate within the limits 2 to 4 with element size of 1. So let us say this is my domain 2 to 4 with element size of 1 means in the middle we are going to have a node which is of 3. So this is my element 1, this is my element 2. So all this is in the x direction. So what I am going to have to do is integral of f of x from 2 to 4 dx. So this I am going to split into 2 based on the element discretization, plus 3 to 4 f of x dx. Okay. So this I call it as I1, this I call it as I2. So what I am supposed to do, I am supposed to use the Simpson's rule to find out the values of I. So this total is I, which is nothing but I1 plus I2. So I use the Simpson's quadrature rule to find out I1 and I2, and then I just add them to find the final answer. So Simpson's rule I again recall. So we have h by 6 into, you can say, f of a plus 4 times f of a plus b by 2 plus f of b. So this is my formula. So for I1 you can say that your h is 1. So because for the first element my element size is 1, f of a is nothing but f of 2. Okay, so actually I guess it's better to make a table. So I'll just make a table now. So let us find x, f of x and element. So for element 1, okay, not this way, I'll rather put it out as a, b. So a, b, f of a, f of b, I put it this way. So for element 1, what is my a? 2, my b is 3, integral from 2 to 3. What is f of 2? F of a is f of 2. So I will just use a calculator. I forgot one more thing. F of a plus b by 2. Okay, so f of 2 is nothing but 2 into 2 cube, which is equal to 2 into 8, which is 16, minus 4 into 2, 8. 16 minus 8 is equal to 8 plus 1, which is 9. What is f of b? F of 3. F of 3. 3 cube 27 into 2, which is 54, minus 4 into 3. So 54 minus 12, which is 42, plus 1, 43. So now f of a plus b by 2.
F of B is 4.
F of b is
4. 4.
4.
X is equal to 4. Right? We've taken x is equal to t.
See, yeah. Actually, if you see, a is the end nodes. Okay. Okay. I get your point. So actually, what we are doing is we are taking element size 1 means we are splitting into 2 elements. So now each element, this will be the end nodes. So another, there will be a mid node which will be at 2.5 and 3.5. Actually, if you see the question, I'm not using this thing element size of 2. Element size of 2 means I will have a single element with 2 end nodes and one midpoint node. So that is how we formulated this thing. So this is actually one element if you see in this question. So I
Right,
highlight.
right.
Yeah. So this is not two elements actually. So quadratic. So we saw that Simpson's rule is a quadratic interpolation. Quadratic interpolation means you have one element with two nodes at the end and one node at the center. So in a similar way, you can say that I'll now switch to the this one. So you can say that you have two elements here. So your domain is from 2 to 4. So you are splitting it into two elements, which means that you have two elements. The endpoints of the first element are 2 and 3. Similarly, the endpoints of the second element are 3 and 4. So midpoint will be at 2.5 and 3.5. So I hope there's no confusion. So this is how it is done. So f of a plus b by 2. So 2.5. So 2.5 cube I calculate is equal to into 2, then minus 4 into 2.5 plus 1. So it is 22.25. So for element 2, my a is b, my b is 4. Sorry, my a is 3, b is 4. A plus b by 2 will be 3.5. So f of a is nothing but f of 3. F of 3 already calculated, so it will be 43. F of 4 we have to calculate. 4 cube, which is 64, into 2, which is 128. 128 minus 16, 4 into 4 is 112 plus 1, which is 113. So f of 3.5 I am going to calculate. Actually, it's better I would have added one more thing. Maybe I'll add it here only. This is my a plus b by 2. This is 2.5, this is 3.5. This is for 1, this is for 2. So f of 3.5. So 3.5 the whole cube into 2 minus 4 into 3.5 plus 1, 72.75. So I have now calculated for element 1 and element 2. Now I just have to do the apply the Simpson's rule for each. So for SR for 1, so h by 6, which is 1 by 6, because h is equal to 1. F of a is 2, sorry, not 2, it's 9. I'll write the formula itself. F of a plus 4 times f of a plus b by 2 plus f of b. So this is 1 by 6 into, what is my f of a? For the first element it's 9. F of b is 43 plus 4 times of 22.25. So I'll just quickly calculate this. Plus 43 plus 9. This is 47 by 2. 23.5. So similarly, SR for the second. So again 1 by 6 into f of a 43, f of b 113, next 4 times of 72.75. So 4 into 72.75 plus 43 plus 113, 447 by 6, 74.5. So finally I 1 plus 2, 23.5 plus 74.5. How much is this? 98. So we'll go to the PowerPoint once more. So answer is 98, isn't it? Yes. So answer is 98. So we'll see how far this is true with the exact integral. Exact integral, I try to do it here only. So integral of 2 to 4, 2x cube minus 4x plus 1 into dx. This will be 2 times of x cube dx, x power 4 by 4 from 2 to 4 minus 4 times x dx, x square by 2 from 2 to 4 plus dx, which is x power 4 by 4, 2 times 4 power 4 by 4, which is 4 cube, 64 minus 2 power 4, 2 power 4 is 16 by 4, which is 4 minus 4 times x 4 power 4 square, 16 by 2, 8 minus 2 square 4 by 2, which is 2 plus 2, 4 minus 2, 60 into 2, 120 minus 4 into 6, 24 plus 2, which is 122, 24. This is also turning out to be 98, I think. Okay, is it not? Yeah. So in this case we find that Simpson's rule, we are getting exact solution as the exact answer. So we can say in general, since there is a quadratic interpolation used, so it is in general more accurate than the trapezoidal rule, which uses linear interpolation. But it's not the case that always you will get the exact value. In this case somehow we got the exact value, but it need not be the case always. Okay, so is there, I hope there is no doubt in this question. So shall we proceed to the next one? So we saw here the answer we got 98 was from the Simpson's rule. Again we got it for here also. So what we will try, maybe before going to the previous, we will just use a single element with 2 and 4 and 3 as the midpoint. Instead of 2 elements, we discretized our domain into 2 elements. Now it's just single element. So now the value becomes h by 6 into f of, sorry, we'll see what the answer comes out to be. Yeah. F of 2 plus 4 times of f of 3 plus f of 4. So mind you, this time my h is 2, so which is 2 by 6. What was f of 2? We'll just see here. My f of 2 was 9. My f of 4 was this one, I guess, 113. Four times f of 3. What's f of 3? 43. So this will go. So 2 by 6 is 1 by 3. So I'll just add this 43 into 4, which is 172 plus 113 plus 9, 294 by 3. So this is also 98. So we used Simpson's rule for a single element. At the same time, we used the Simpson's rule for two element also. So two element in the sense you have 2, 3, 4. So at each you have a midpoint which is 2.5 and 3.5. So here you had only single element. Here you had two elements. So this is 1. This is 2. So in all the cases we are seeing the answer is coming out to be 98. So this need not always be the case as I mentioned. However, since the polynomial here is a simple polynomial, the answer turns out to be correct. So we'll go to the next question now. Okay, this is a straightforward question. So how much would the length of a 1D element, how much would be the length of a one-dimensional element in the natural coordinate system? So there are four options given.
H by 2.
Sorry, it's 2. This one?
H by 2.
Oh, h by 2. Okay. I'll erase this. So how much would be the length of a one-dimensional element in the natural coordinate system? So do you have any idea what's a natural coordinate system? So you can try to recall from the week 3 lectures. So natural coordinate system. So let us say this is my element, and let us say I am going in the x direction. This is xa and this is xb. So let us say the element is h. So is this a natural coordinate system? So this is an x coordinate system. So is this natural?
No.
Okay. So natural is you have a coordinate system where you have the coordinates varying from a maximum to minimum of -1 to maximum of +1. We call this as zeta coordinate system. So here what is the length of the element in this? So this is +1, this is -1. So here you can say the length is nothing but xb minus xa, correct? In this coordinate system the length is nothing but 1 minus of -1, which is 2. So answer is B. So as highlighted here, answer is B. So any doubt? So answer is not h by 2 actually, answer is 2. So why is? Because we have a straight in the zeta coordinate system, the limit coordinates are -1 to +1. So the distance between both is 2. Is it fine?
Yes.
Okay. So this is the fifth question. So we'll go to the next question. Okay. For the linear transformation of the form x is equal to a plus b times of eta, that maps a 1D element from the normal coordinate system to the natural coordinate system as shown below. So what I have drawn here is what here is also being shown here. So for this linear transformation from x to eta, so what are the values of a and b? So this is the x is equal to a plus b times of eta, that maps the one dimensional element from normal coordinate system to natural coordinate system. So what are the values of a and b? So if you already know the answer, you can guess. Otherwise we'll try to work this out. For this purpose I will again go to the note section. It's easier to write here. So this is our sixth question. So which means I have an element which is in the, sorry, this is xa, this is xb. This is my normal coordinate system x, and this I am going to map it to -1 to +1. This is a natural coordinate system. So natural coordinate system, always your extreme points are -1 to +1 for a, for this straight line element. So your mapping is x is equal to a plus b times of eta. So this is a linear mapping. So how we are going to map? So you have 2 points. So at x is equal to xa, what is the value of eta? So corresponding to xa, your eta value is -1. So which means I am going to substitute xa is equal to a plus b times of -1, which is equal to a minus b. So this is my first equation. At x equal to xb, this is my second point. So my eta is +1. So same I am going to substitute xb is equal to a plus b times of 1, which means it is a plus b. So this is my equation 1, this is my equation 2. So xa and xb you have. So what I can do, I can add both the equations. So I get a plus a minus b and a plus b, b cancels out. I get 2a is equal to xa plus xb. So a is equal to xa plus xb by 2. Correct? So I can substitute this a in any one of the equations, I can get the value of b. So let us say I am substituting in xb, second equation, xb is equal to a plus b. So a is xa plus xb by 2 plus b. So b I have to subtract. So this becomes xb. Okay, think. Yeah, xb minus xa by 2. So we have got values of both xa and xb. So sorry, a and b. So a is xa minus xa plus xb by 2, b is xb minus xa by 2. So we'll check the options now. So answer is, you can say it's option B. Correct? So we just solved what is A and B. Okay. So shall I proceed to the next question? So this is a linear mapping. So from the normal coordinate system at which is based on x to the natural coordinate system which is based on eta. So we use a linear transformation in the form of x is equal to a plus b times of eta. So this maps the element from the normal to the natural coordinate system. So the values of a and b were the question. So we just solved how to get the a and b. So we'll go to the next one now. Okay. So question 7 is, compute the approximation functions for a 3-noded element shown below using the Lagrangian family of interpolation functions. So can anybody tell what is a Lagrangian family of Lagrangian family of polynomials basically? So what are the any characteristic properties of the Lagrangian polynomial?
Time independent.
Sorry?
Time independent.
Oh, time independent. Okay. So okay, that could also be the case, but in okay, I'll put it this way. So basically, if you have two points through which, so let us say a and b, through which you are going to interpolate a function. So using 2 points, the best polynomial, best degree of polynomial you can get is a linear polynomial, obviously. So let us say my linear polynomial is f of x is equal to some format. Let us say it's mx plus c or something. So what happens is, if it is a Lagrangian polynomial, my value at a, so I have two polynomials, I can say f1 and f2. So if my f1 will be is equal to 1 at a and it will be 0 at b, and similarly my f2, this is f1 of x, and similarly this will be the case for f2. So it will be 0 and 1 here. So this is one of the properties of the Lagrangian polynomial. So Lagrangian polynomial is, if you have n data points, then you will have n Lagrangian functions, and the value of the Lagrangian function corresponding to a data point could be characterized in this way. So if you have f of I of x of j, you can say this is delta ij. This is nothing but a Kronecker delta function. So this is 1 if I is equal to j. This is 0 if I not equal to j. So which means f1 of x1 is equal to 1, f1 of x2, f1 of x3, f1 of x4, all these values is going to be 0. So which means your f1 is 1 only at x1, and all other values will be x2. Similarly, your f2 will be at 1 only at x2. At x1, x3, x5, all other things, f2 will be 0. So this is the important property of a Lagrangian function. So how can we generalize this Lagrangian function is, so this is also you could have seen in the lecture. So Lagrangian function, let us say p of pi of x is equal to, so you can say this is a product. So I varies from n, I not equal to r, you can say. Maybe I'll write it as pr of x. So this is x minus, sorry, x1, sorry, I'll erase this. So I already put this x minus xi by xr minus xi. So here xi, if obviously if I is equal to r, then xr minus xr becomes 0 in the denominator, so this becomes undefined. So we have to avoid this. So I not equal to r. So if I write in this way, so if I want to expand it, so you can write as x minus x1, x minus x2. So except x minus xr I should not have. You can say x minus x r minus 1, then x minus x of r plus 1. Sorry, this plus I should avoid. So all multiplication, product x minus xn. So rest of the things xr minus x1, xr minus x2, xr minus xr minus 1, x minus x r plus 1, xr minus xn. So this is the Lagrangian polynomial. So I hope till here there is no doubt. So this you would have already seen in the lecture classes. So now we have to compute the approximation functions for a 3-noded element. Okay. So we have 3 nodes. I'm going to do that. Minus 1, 0, 1. So this is my point 1, this is my point 2, this is point 3. So P of, so you can say eta minus eta I, eta r. So you can say P1 eta, eta minus eta 2, eta minus eta 3 by eta 1 minus eta 2, eta 1 minus eta 3. So we'll see eta 1 is minus 1, eta 2 is 0, eta 3 is 1 plus 1. So if I substitute these values, will be eta minus eta 2 is 0, eta minus eta 3 is 1, eta 1 minus eta 2, minus 1 minus 0, minus 1 minus 1. So this is minus, so minus 2 into minus 1, which is plus 2, epsilon into epsilon minus 1, p1 of epsilon.
What is eta r?
Eta r you are asking?
Yes.
So r is nothing but any variable which could be between 1 to n. So it could be so
How did you write eta r as eta 1?
eta r as
Eta 1.
see, basically we have r, we have totally, so this n is the total number of polynomials. Okay, so r is nothing but it can anywhere between 1 to n. So you can have p1, you can have p2, you can have p3, and so on. You can have pn. So this r is nothing but just an indicator variable. So it can be anywhere. So this I to 1 to n, this is nothing but it's a product. So from n terms you are going to multiply. But it's not just n terms, it will be n minus 1 terms because your I not equal to r. So that is a very important case. So here what you can see is, so here my n is equal to 3. Since I have 3 points, I have 3 polynomials. Okay, so the first polynomial will correspond to minus 1, the second polynomial will correspond to 0, the third polynomial will correspond to plus 1. So this is the formula for p1. So which means I could have multiplied eta minus eta 1 also, but that I should not do because I have the condition I not equal to r. So if I have eta minus eta 1, then I should have eta 1 minus eta 1 in the denominator also. That will make my polynomial undefined. So I am restricting to n minus 1 terms, which is the 2 terms in the numerator and denominator. So r here corresponds to 1, and the multiplication goes from I to n excepting the I is equal to r. So that is how we arrive at this, and eta is nothing but a natural coordinate system. So this coordinate system, so between minus 1 to 1. So is it okay?
Yes.
Okay, so p1, again I am going to calculate p2. P2 means I am going to avoid 2, epsilon minus epsilon 1, then sorry, eta minus eta 3. So here I am going to have 2, eta 2 minus eta 1 into eta 2 minus eta 3. So if you carefully observe the formula, if p1 p2, so in the numerator you will not have 2 term, while in the denominator you will have 2 term instead of eta. So eta will be replaced by eta 2. So that is the case. So similarly p1, if you see it, you don't have one term, eta 1 term in the numerator, but in the denominator the eta will be replaced by eta 1, the same structure. So if I have to substitute eta minus eta 1 is minus 1, so again you have to refer to this diagram. Eta, this is 1, this is 2, this is 3, and the values are minus 1, 0 and plus 1. Eta minus eta 1, eta minus eta 3, so this is plus 1, so minus plus 1, which is minus 1. So eta 2 0 minus of minus 1, then this is 0 minus 1, so which means this is plus 1, this is minus 1. So you have minus in the numerator, rather denominator, it goes up to the numerator, eta plus 1 into eta minus 1. So this is minus of eta square minus 1. So this becomes 1 minus eta square. So now p3 will be eta minus eta 1 into eta minus eta 2. So 3 I am avoiding, so 3 will be replaced here, eta 3 minus eta 1, eta 3 minus eta 2, eta minus 1, eta minus 0, eta 2 is 0, then similarly here 1 minus of minus 1, 1 minus 0. So this is be half into eta plus 1 into eta. So if we summarize the polynomials, P1 was, let us see, half eta of eta minus 1. P2 was 1 minus eta square. P3 was half eta to eta plus 1. So this we have solved the answer, but just for further understanding, we will try to see what are the properties of this P1. So P1 at eta is equal to minus 1 is equal to half into minus 1 into minus 2. This is 1. So P1 at eta is equal to 0. This will be 0. So P1 at eta is equal to plus 1. This will also be 0 because 1 minus 1 0. This will be 0. P2 at eta is equal to minus 1. It will be 0. P2 at eta is equal to 0. This will be 1. P2 at eta is equal to 1 will be 0. So you have to substitute. Similarly P3 at eta is equal to minus 1. So minus 1 plus 1 0. This will be 0. P3 at eta is equal to 0, again 0. P3 at eta is equal to 1, which is half into half into 1 into 2, 1. So again if I try to plot, minus 1 0 1, let us plot it this way. So P1 it will be 1 and rest of the values it is 0. So it will be quadratic, so something like this it will be. So it will be 0. This is P1. So P2 will be 1 at this point and it will be 0 at here. So something like this. P2. P3 will be 1 at this point and will be 0 at this point. Something like this. So again we saw, right, in the previously. So f1 will be 1 only at x1. At all other points it will be 0. Similarly here if you see P1, it is 1 at this first point. So this point 1, point 2, point 3. So coordinates are minus 1 0 plus 1. At first point P1 is 1, at second and third point it is 0. Similarly P2 is 0 at first and third point, it is 1 at second point. P3 is this one. Oh, this is P2 I mean. This is P3. P3 is 0 at both first and second points and it is 1 at third point. So this is the Lagrangian polynomial. So to summarize the answer here, P1 was half into epsilon into epsilon minus 1. P2 is 1 minus epsilon square. P3 is half into epsilon plus 1. Okay, so shall we go to the next question? So these are the approximation function, P1, P2, P3, Lagrangian family. So can we go to the next question? Okay, I hope there's no doubt. Okay, so this is question number 8. So what does shape function represents? So there are four options. So shape function represents first approximation of geometry. So second function is approximation of unknown primary variable. Third option is both, it represents both a and b, and the fourth option is it represents neither a nor b. So can you guess?
Both A and B.
Okay, both a and b. Okay, actually this is a, this question is you can say uh, the answer is actually unambiguous, ambiguous. So in some cases they consider only for geometry, in some cases they are consider both approximation of geometry and unknown primary variable. So what in our lecture they have mentioned is it's option A, but in some cases it can be both A and B. So basically what it means is you have some primary variable u, which is you are going to represent I is equal to, sorry, go to erase this, I is equal to 1 to n ui psi I, something like this, and you are going to again approximate x is equal to I is equal to 1, so j is equal to 1 to, or let us say xj psi j. So in both the cases you can see there are some approximation function used. So these can be called approximation or interpolation function. So but in one case, in both the cases you can call shape function, but since x represents the geometry, which is the coordinate geometry, we are specially calling these functions. So these functions which are associated with x, these are alone called shape functions. But in general, if you refer to some other you know uh, for finite element this thing, so they will represent both as shape functions, because shape function is just interpolates, they call shape function, it is used as a alternative to interpolation function also. So basically it interpolates the primary variable or the solution between the nodal points. So one can say depending on the situation, both a is also correct, you can say both a and b are also correct, but what in our lecture is this, in our lecture contents, if you would have seen, only the geometry approximation is named as shape function, rest are just called either approximation or interpolation function. Is it okay? So even C can be right, that's what I am trying to say. Shall we go to the next?
Yes.
Okay, just a minute. Okay, now we are going to come to the concept of Jacobian. So the value of the Jacobian computed for the linear order transformation from the normal to the natural coordinate system for the element. So are you aware of what Jacobian means? So this is again once again a transformation from the points from the normal coordinate system to the natural coordinate system. So there is a Jacobian which is associated with it. So we'll just see how the Jacobian is defined before going. So J is called Jacobian. This is nothing but you can say it is dx, you can call it dx by d eta into d eta. So this is like chain rule, you can say. So this is nothing but Jacobian. So dx is equal to j times of d eta. So this is Jacobian. So how we are going to find the Jacobian? So you need to find x as a function of eta. So how do we find that? So if you already see the last few questions, we would have already found x as a function of eta for this. So we found that x is equal to a plus b times eta for a linear transformation, and values of a and b are given. So I am going to just directly take this. So my a is equal to, so let us first write x is equal to a plus b times of eta. A is equal to x xa xb by 2 b is, again we'll go back, check, xb minus xa by 2. I'll go to the notes, that is more easier to write. So basically I have a natural coordinate system. I'm going to transform it into the, so from normal coordinate system to the natural coordinate system, x to zeta. So this we saw that this x is equal to a plus b times of zeta. A is equal to xa plus xb by 2. V is equal to xb minus xa by 2. So this we saw from the previous question, I mean one of the previous questions. So I'll just substitute x is equal to xa plus xb by 2 plus xb minus xa by 2 into eta. So this is x is a function of eta. So now what is my Jacobian? Jacobian is dx by d eta. So if I differentiate this expression with respect to eta, so this will vanish and this constant will remain, xb minus xa by 2. So this is my Jacobian. So what is the answer? Answer is D, xb minus xa by 2. So any doubts? So this is a linear transformation and we found out the magnitude of the Jacobian associated with this transformation. Okay, so we'll go to the next question. So sorry, any doubt in the previous question? So Jacobian is always defined as dx by d eta. So this is how we define, which is means dx to d eta transformation is through Jacobian. X to eta transformation, we have a function and the differentiation of that function x dx by d eta is gives us the Jacobian. Okay, so this is question number 10. So for a typical Euler-Bernoulli beam FEA problem, so if you recall, it would be something like minus d square by dx square of ei d square x by d, sorry, d square, it's not x, it should be some deflection which is w. So primary variable is w, you can say. W by dx square is equal to some q. So something like this you might have seen for the Euler-Bernoulli beam. So interpolation functions for the primary variable are given to be cubic order, and the transformation, so the transformation from the normal to natural coordinate system is to linear shape functions. So what is this kind of a formulation? So there are four options. Option is subparametric, Option B is isoparametric. Option C is superparametric. Option D is cannot say. So any guess as to what could be the answer? So I have listed the Euler-Bernoulli beam this equation, and we have said that W, the primary variable, is approximated through cubic order functions, and the transformation is through approximated through linear shape function, the geometry. So what's the answer? Any guess? So is it A, or is it B, or C, or D? Any guesses? Okay, so we'll see. Look at the answer. Answer is option A. Option A, subparametric. So actually here we have to define what is the three types of formulations. You can see the subparametric, isoparametric, and superparametric. So let us say that you have a order of interpolation of primary variable at one side, then order of interpolation geometry. So let us say this is some m, this is some n. So if m is greater than n, so this could be subparametric. So if m is equal to n, this is a isoparametric. So if m is less than n, this is superparametric. Or you could say, sorry, or you could define it either way. So order of interpolation of geometry, if it is m, and if this order of interpolation of primary variable is n, then you can define it the other way around. So here I am defining the order of interpolation of primary variable as m, the order of interpolation of geometry is n. So here m is greater than n. Since this is a cubic order, it's a third order, and shape function is linear order, which is first order. So m is greater than n, so obviously the answer is subparametric. So we'll go to the question 11 now. So again, this is a theoretical question. So which of the following numerical integration schemes involves unequally spaced quadrature points? So four options are given. Option A is the trapezoidal rule. Option B is Simpson's rule. Option C is the Gauss-Legendre rule. Option D is none of the above. So to solve this answer, we need to know what are the formulas of each of the numerical integration scheme. For trapezoidal rule, we have already discussed earlier. So you have an element a to b. So this integral is dependent only on endpoints. Suppose we have lot of elements, so 1, 2, 3, and so on. So for element 1, you can say TR is, so each element is h by 2 into f of a plus f of b. So for second, it is h by 2 into f of b plus f of c. For third element is h by 2 into f of c plus f of d. So if you add all, you will get h by 2 into, so f of a is counted as 1, f of b is counted twice, so it's 2 times of f of b. Again f of c is counted 2 times, so 2 times of f of c plus f of d. So this is your general. So if there are n elements, you can say that the first element and the first node and the n plus 1th node will be represented one time, and rest all the middle elements will be represented 2 times. So if you see in this trapezoidal rule, you can say that all the quadrature points are nothing but the points at which the functions are evaluated. So function is evaluated at a, functions evaluated at B, functions evaluated at C, functions evaluated at D. So all these quadrature points are equidistant. So trapezoidal rule cannot be the answer. So let us move to Simpson's. So in Simpson's rule, if you take for one element A and B, and the third element is actually at the midpoint A plus B by 2. So this is one element. So second element, you have C, means it will be B plus C by 2. So if you add up everything for this element, you can say this occurs one time, this occurs one time, this occurs 4 times. So if you see, it will be h by 6 f of A plus 4 times of f of A plus B by 2 plus f of B. For second, it will be h by 6 f of B four times f of B plus C by 2 plus f of C. So if you add everything, you will see that for both the elements h by 6 f of A plus 4 times of f of A plus B by 2 plus 2 times of f of B. So here f of B, here f of B, then again you have 4 times of f of B plus C by 2 plus f of C. So if you see here, you can see that the end points, so the extreme points A and C occur only once. The midpoints of each element have 4 times, and this happens 2 times. So in all these cases, if you see all the quadrature points, so integration points are on A. So function is evaluated at A, function is evaluated at midpoint, function is evaluated at B, function is evaluated here also, and here also you can see the function is evaluated. So in all put together, all will be equidistant. So you can say this will be h by 2. Similarly, this will also be h by 2. Okay. So this is also not a correct answer. So if you see element wise, it is fine. So equally spaced quadrature points for both trapezoidal and Simpson's rule. For Gauss Legendre, if you see, actually it is unequally spaced. So why is this unequally spaced? So for that we need to know what is Gauss Legendre. So we'll see that. Okay, I'll rather do it in this notes. So how do you define what is Gauss Legendre? So Gauss Legendre, in the sense, you have a function f of x from A to B. So this will be the trapezoidal rule. Let me draw this in red color. This is this one, trapezoidal, since a linear interpolation, and if you have something like this at a plus b by 2, so you have a quadratic something like this. So okay, I'll rather redraw this entire thing. So this will be my trapezoidal rule, the interpolation for this one. You have another point, you have 3 points, so this will be some quadratic interpolation, Simpson's. But what about Gauss Legendre? So Gauss Legendre will be, you will be integrating it at 2 points, but they are not on the mid, they are not on the this one. You can say they are not at the end points a and b, so they will be somewhere around here, and you are going to have based on that some thing, something like this. So how, that is a graphical representation. So basically how we are going to evaluate Gauss Legendre is, so this is for the natural coordinate system. So if you have anything for function f of x dx, so this can be some approximated as summation from I is equal to 1 to n f of xi f of xi into wi. So these are the quadrature weights. These are quadrature points. So you can observe that in Gauss Legendre it is not necessary for xi to be equally spaced. So in trapezoidal rule we have 2 points which are equally spaced. In Simpson's rule we have 3 points that are equally spaced, but in Gauss Legendre we need not have, it can be the points can be somewhere here and here, but if you see this distance, this distance need not be equal, so this is unequally spaced. So answer is C. Is there any doubt? Okay, so we'll go to the next question. Which of the following is not true for the Gauss Legendre quadrature? Okay, again we just saw in the last example that our quadrature points are actually somewhere here. These two are the quadrature points, and it is not at the end nodes. So which means obviously the quadrature points and end node are not same. So here itself we can say that option A is the answer, but for the sake of understanding, let us see about other points as well. The quadrature points are unequally spaced. Yes, this is true. We saw last point we saw, and as the number of quadrature point increases, accuracy also increase. This is also true. So more the number of quadrature points, the more the number of places where the function is evaluated. This means the integral accuracy will be obviously increased. So these both are true. This alone is false. So option is answer A. So as as seen here, option is answer A. So let us go to the next question. So the quadrature points associated quadrature weights associated with a 2-point Gauss Legendre formulation. Okay, so this needs some working out actually. We'll try to work out now. So we'll see what is Gauss again Gauss Legendre. I'll again redefine. So minus 1 to 1, if you have something called f of eta d eta, this can be summation from I is equal to 1 to r f of eta I into wi. Okay, so firstly let us have a 1-point Gauss Legendre. So 1-point Gauss Legendre means r is equal to 1, so which means f of into w1. Okay, so you have two unknowns. This one chi 1 sorry eta 1 and w1 are two unknowns. So for two unknowns you need basically two terms, you can say. Okay, I think somebody has joined. Okay, so we have two unknowns and you have two terms, so you need two terms, which means if you were to integrate a constant function, or you can say you are to integrate a linear function, then you can get a quadratic. So two unknowns, which means we need two data points. So between two data points you can have a linear order. So that linear order f of epsilon, I am going to represent it as a plus b times of epsilon. Sorry, this is again not epsilon, it is eta. So a plus b times eta. So integral of minus 1 to 1 is equal to f of eta 1 into w1. So what is f of eta 1? A plus b times of eta 1 into w1. So I am going to integrate this a times of d eta, a times of eta minus 1 to 1 plus b times of eta square by 2 minus 1 to 1 is equal to a w1 plus b w sorry eta 1. Okay, so if I were to do this 1 minus of minus, this becomes 2 times a plus this vanishes, b times of 0 is equal to w1 a plus w1 eta 1 into b. So we have this. So for this to be true, for the above relation to be true for all a and b, so the coefficients should match. So which means w1 is 2, so these two terms should match and these two terms should match. So if b is the coefficients of b, 0 is equal to w1 chi 1. So chi 1 is already 2, so your w1 is 2, so eta 1 is 0. So which means that integral of minus 1 to 1 f of eta d eta is equal to, for 1 point it will be f of 1 into w1, where eta 1 is 0, weight is 2. So let us do for 2-point quadrature now. 2-point Gauss Legendre quadrature. So 2-point means you have f of w1 plus f of eta 2 w2. In this we have 4 unknowns. So which means at the best we can try to get 4 data points, which is possible for a cubic interpolation. Let f of eta is equal to a plus b eta c plus d eta cube. I am going to integrate this from -1 to 1. F of eta 1 w1 plus f of eta 2 w2. So if I integrate a, so like this I am integrating. F of eta 1 is a plus b eta 1 plus c eta 2 square sorry eta 1 square plus d eta 1 cube, the whole multiplied by w1 plus f of w2 is a plus b eta 2 plus c eta 2 square plus d eta 2 cube, the whole w2. So a, the coefficient is 2, for b it's going to be 0, plus c is going to be 2 by 3, plus d is going to be 0. If you just plug in the values, then for a it's going to be here w1 plus w2 plus b you have w1 chi 1 epsilon 1 eta 1 plus w2 plus c w1 square plus d cube. So again, for the above relation to be valid for any value of a, b, c and d, so you have to match the coefficients. So this gives us 4 relations. W1 plus W2 is 2, W1 eta 1 plus W2 eta 2 0, W1 eta 1 square plus W2 eta 2 square is equal to 2 by 3, W1 cube plus W2 is equal to 0. So we have to solve this equation. So how do we solve it? Okay. So I'm going to multiply, so I'm going to name it as 1, 2, 3, 4. So 1 I'm going to multiply with eta 1, w1 eta 1, w2 eta 1 is equal to 2. So here again I'll take the equation 2 as it is, w1 eta 1 plus w2 eta 2 is equal to 0. So if I subtract both, I'll get w2 into eta 1 minus eta 2 is equal to 2. I think I'm right. Okay. Yeah, these both will cancel. Yes, if you subtract this, you will get this. So now I'm going to take equation 2 and multiply it with eta 1. So I'll get w1 eta 1 square plus w2 eta 1 eta 2 is equal to 0, and equation 3 I am going to take as it is, w1 eta 1 square plus, okay, w2 eta 2 square 2 by 3. I am going to subtract both, so which means these two terms will vanish, so w2 into eta 2 square minus w2 eta 1 eta 2 is equal to 2 by 3. So if I take w2 eta 2 common, eta 2 minus eta 1, 2 by 3. Okay, so if I divide this both, w2 into eta 1 minus eta 2 by w2 eta 2 into eta 2 minus eta 1, 2 divided by 2 by 3, 2 into 3 by 2, so this is 3. I think 2. Okay, I think I forgot one thing. Epsilon 1, I forgot to put 2 epsilon 1 here. So which means this you will have epsilon 1 here. Okay. Then you have to see whether there is any mistake here. 0. Okay, 2. Okay, this will be minus 1. This both will go. Minus 1 by epsilon 2 is equal to 3 epsilon 1. This is what I am getting. Okay. Let us check once more all the equations. 2 0. Okay. Okay, I'll do one thing. I'm going to erase everything. I'm just going to, I think I made a mistake somewhere, that's why. So I'll recalculate. The 4 equations, I'm going to multiply first equation by epsilon 1. W1 epsilon 1 plus W2 epsilon 1 is equal to 2 epsilon 1. So W1 epsilon 1 plus W2 epsilon 2 is equal to 0. So subtract both. W2 into epsilon 1 minus epsilon 2 is equal to 2 epsilon 1. Okay. So with this, so again I am multiplying first equation epsilon 1, what do you want? Epsilon 1 square plus W2 epsilon 1 epsilon 2 is equal to 0 into 0, W1 epsilon 1 square plus W2 epsilon 2 square, 2 by 3. So I am going to subtract both. W2 into epsilon 2 epsilon 1 epsilon 2 is equal to minus 2 by 3. Okay. So I divide both. W2 into epsilon 1 minus epsilon 2 minus 2 by 3. Okay. So which means this is, I got a relation between epsilon 2 and epsilon 1. So which means 3 epsilon 1 epsilon 2 is equal to minus 1. So I am substituting this in third equation. W1 epsilon 1 square plus W2 into, okay, not third equation, rather I will substitute in fourth equation. So epsilon 2 minus 1 by 3 minus minus 320. Okay. W2 by W1. Okay, W1 epsilon 1 plus W2 epsilon 2 is equal to 0. W1 epsilon 1 plus W2 into minus 1 by W1 epsilon 1 is equal to W2 by 3 epsilon 1. So which means 3 epsilon 1 square is equal to W2 by W1. W2 by W1 is 3 epsilon 1 square. Okay. So finally, if you solve everything, you will get W1 is equal to W2 is equal to 1, and sorry, not W1, yes, equal to 1. Chi 1 is equal to minus 1 by root 3. Chi 2 is plus 1 by root 3. So if you go to this, so answer will be B. So it's just a matter of solving the 4 equations. If you solve everything, you will get W1 W2 as 1 and epsilon 1 and epsilon 2 as plus or minus 1 by root 3. So these are the two quadrature points and the two associated quadrature weights of the Gauss Legendre. So if you plot a table, actually, if you say R, so 1 point, 2 point, 3 point, so what are the chi I, what are the Wi? So here chi I will be 0, it will be 2, here it will be plus or minus 1 by root 3, here it will be 1. Here similarly you can say you will have three things. You will have plus or minus root over 3 by 5. For this you will have 5 by 9, and 0 you will have 8 by 9. So this you can construct similarly for 4, you can construct the Gauss quadrature table by the way we did for 1 and 2. Okay, we will go to question number 14. The minimum number of quadrature points recommended for numerically integrating a polynomial of order 5 to get exact solution. So can anyone guess the answer? Polynomial is order 5, so you have to integrate a polynomial of order 5. So general rule is, if order is, so let's say n is your order, so if n is odd, then your P, the minimum number of quadrature points required, is n plus 1 by 2. If n is even, P is equal to n by 2 plus 1. Okay, so here n is odd, so 5. So 5 plus 1 by 2, which is 6 by 2, you can get answer is 3. So you can say that the minimum number of quadrature points recommended for numerically integrating a polynomial of order 5 to get exact solution. So our answer is 3. So we have one final equations before we wind up the session. So we are going to evaluate integral from 10 to 4. We will evaluate here integral from 4 to 10. What is the thing? X plus 3x square plus x power 5. Okay, so using Gauss Legendre, so 4 10, this is our normal coordinate. We have to first step is you have to convert it into a natural coordinate. So how we are going to do this? So this is xa, xb. So actually your x is equal to xa plus xb by 2 plus xb minus xa by 2 into eta. 4 plus 10 14, 7 plus 3 eta. So this is your x. X is equal to f of eta. So this is a capital F of x. So which means integral 4 to 10 capital F of x dx is equal to integral minus 1 to 1 f of x of eta d j times d eta. So we already saw Jacobian is dx by d eta. So Jacobian is going to be, if you, this is your x with respect to eta. So if you differentiate, j is equal to 3. Okay, so j times of d eta. So this whole thing you can say it as capital G of eta. So any integral from minus 1 to 1 g of eta d eta. Is equal to, you can say summation I is equal to 1 to r g of eta r, sorry, eta I into wi. So what is the order of g of theta? That will be order of f. What is the order of f? It is fifth order. So we just saw in the last question, for fifth order we need three things, three, what you can say, quadrature points. So which means f of x of eta 1 into j into w1 plus f of x of eta 2 into j into w2 plus f of x of eta 3 into j into w3. So eta 1 you can say it is minus square root of 3 by 5, eta 2 is 0, eta 3 is square root of 3 by 5. W1 is 5 by 9, W2 is 8 by 9, W3 is 5 by 9. So J is 3 we saw, and W1 we saw, we have eta 1 W1. So what is x of eta? We just saw it is 7 plus 3 eta. So x of eta 1 is equal to 7 plus 3 eta 1, which is 7 minus 3 root of 3 by 5. X of eta 2 is equal to 7 plus 3 times of eta 2, which is 7, because eta 2 is 0. So x of eta 3, 7 plus 3 eta 3, 7 plus 3 square root of 3 by 5. So we will calculate what is x of eta 1. This is x1. So this thing we are going to calculate. It comes out to be 4.6762. Similarly, x of eta 2 is 7. X of eta 3, you can get 9.3238. So I am going to calculate f of everything. So capital F is x plus 3x square plus x power 5. F of f1 is f of 4.6762, f2 is f of 7, f3 f of 9.3238. So I have the formula here. So this is my formula. F of x1, j is common. J is common for everything. So j is common into f of f1 w1 plus f2 w2 plus F3 W3. So you can calculate F1, F2, F3. Finally you can say that so let us say I'm including J everywhere. Instead of taking common, and this will be I1, I2, I3. So I1, if I calculate, I will get it to be 3843.7. I2, if I calculate, I will get it to be 45229. I3, if I calculate, I will get it to be 119890. So finally, if I add everything, that will be my total I value. So that I will get it to be 16696. How much is that? Yeah, it will be something 116960, I think. Or sorry, 1962. If I approximate as 3843. Okay, so this is my value. Okay, so we saw how to solve the problem using Gauss Legendre. So I think we'll stop the session here. Okay. Okay, so I hope we able to recall some of the concepts of the week 3 contents of this lecture series through the sample assignments questions we solved today, and I hope this was of use, and next week we'll meet with sample assignment questions for the week 4 contents. So I think I can close the session now. So any doubts final? Okay, if there are no doubts, I'll now end the session. First I will stop the recording.